Let's calculate some more probabilities with this formal definition. In this example, we have a bag that contains 6 red Skittles, 9 yellow Skittles, and 2 green Skittles. You reach into the bag and without looking and pick a single Skittle to eat. A. What is the probability of picking a red Skittle? With this formal definition, remember, we're going to create a fraction to calculate the probability. And that fraction is going to be in the numerator how many ways we could get a red Skittle. Well, there's 6 red Skittles, so we're going to have 6 divided by, and in the denominator we'd have all of the ways we could pick a Skittle. So in this case, we have to think about how many ways there are to pick Skittles. There's 6 red, 9 yellow, and 2 green. So that's 17 total Skittles we actually could pick from, or it's 17 different options. So I would actually divide my 6 by 17. So the probability of picking a red Skittle is 6 over 17. Now that's the fraction probability. I could convert that to a decimal or a percent. I'm going to concentrate on just the fractions and the decimals, or rather the percents on this page, because the decimal is just kind of the middle point of that. 6 divided by 17 would give me a decimal, and then converting it to the percent would be 35.3%. I'm rounding at the first decimal place, as I mentioned before. Another example, what is the probability of picking a red or a green Skittle? So here we have an or, which means we need to look at all the options of either one of these two things happening. Well, there's 6 red and 2 green, so that's 8 possible ways this could happen out of a total of 17 things in general that could happen. 8 out of 17 is the probability of getting a red or green, or converting that to a percent, that would be 47.1%. Again, I'm rounding at the first decimal point. Next question, what is the probability of picking a Skittle that is not green? Well, if we're not green, we have to be one of the other two colors, and the other two colors are red and yellow in this example. So not being green means everything else. So there are 6 and 9, that's 15 Skittles that are not green out of 17 total options. 15 divided by 17 gives me a percentage of 88.2%. So there's an 88.2% chance of not getting a green. Now this idea of not having something, so not being green, that's something that we often refer to as the complement of an event. So this would be the complement of being green. We often denote a complement, if we want to abbreviate, as the event letter with a superscript of C. So again, the complement of an event would be all events in the experiment that are not that one event, not A. So in this example, the complement of being green would be all things that are not green. The probability of that an event does not occur, in other words, the probability of the complement of an event, can be calculated with a pretty simple formula. It would be calculated as 1 minus the probability of A. Now you might be asking yourself, why 1? Well, remember 1, there's no percentage after it, is the decimal equivalent. If we think about the percentage equivalent of 1, that would be 100%. If we think about that, the probability of an event and its complement when added together, those two things represent every possible thing that could happen. Being green, not being green. If we look at those probabilities together, we're looking at 100%. So the idea here is that when we know one but not the other, we could always subtract one from 100%, one of the two probabilities from 100% to get the remaining probability. So the probability of being green is equal to 1 minus the probability of not being green. Or likewise, the probability of not being green is equal to 1 minus the probability of being green. So we can use this complement rule to actually answer the question we had up above in part C. The probability of not being green is equal to 1 minus the probability of being green. Well, let's take a look at that with this setting. So I have 1 minus. Now to work out the probability of green, I go back to the original data. There are 2 green Skittles out of a total of 17 Skittles in the bag. If I want to do this subtraction, because I have a fraction, I need a common denominator. Generally, we make a whole number and make it into a fraction with that common denominator. 1 can be converted to anything over itself. Since I want a 17 in the denominator, I'll write that as 17 over 17. So 1 is just the same thing as 17 over 17, but now I can go ahead and subtract these two fractions. 17 minus 2 is 15 over common denominator 17. If we look closely at that answer, the probability of not being green is 15 over 17. That's exactly what I had up here. Originally, though, I calculated that by just looking at what was not green, 6 red, 9 yellow. Here I'm calculating it based on this idea of complement, 1 minus the probability of what we're trying not to get. So there's actually two ways you can sometimes find the probability of a complement, or something that is not happening. You could either use the raw data, or you could use this rule related to complements. Where this rule really comes in handy, though, and is essential, is when you don't have the raw data. In our next example, we don't. Suppose the probability of winning a door prize at a charity event is 26%. You attend the event. What is the probability you won't win a door prize? So notice not winning a door prize, that's what won't means. So the probability of not winning, according to our definition here, is equal to 1 minus the probability of winning. And in this case, that's what we know. We know the probability of winning. Now, our probability of winning is 26%. So I'm going to subtract 26%. And here I have a 1 according to the formula. But remember, I want to subtract like entities. 1 is the decimal equivalent. If I'm trying to subtract a percent, I want to convert that to a percent. So 1 is the same thing as 100%. So this would be 100% minus 26, or 74%. So the chance of not winning anything, or winning specifically a door prize at this charity event, is 74%. Let's look at another common way you'll think about games of chance, and that's with cards. So here I have a picture of a standard deck of cards. If you're not familiar with cards, let me just do a little brief overview. In a standard deck of playing cards, there are 4 suits. In this case, we have hearts, spades, clubs, and diamonds. And each suit has 13 cards associated with them. You have 2 through 10. Then we have a jack, a queen, a king, and an ace. An ace is sometimes also thought of as a 1. But there are 13 cards total for every suit. And since there's 4 suits, that means there are 52 cards total in a deck of cards. All right, let's use the deck to actually answer some probability questions. If you want, take a pause here, try answering these all yourself, and then unpause and you can check your answers. All right, I think I gave you some time to pause and then unpause. Let's go through these. What is the probability of drawing a queen? Well, if we look carefully here, there's a queen in every suit. 1, 2, 3, 4. There are 4 queens out of 52 cards. So the probability of drawing a queen can be calculated as 4 divided by 52, which is the same thing as 7.7%. What is the probability of drawing a heart? Well, there are 13 hearts out of 52 cards. 13 divided by 52 is exactly 25%. So there's a 25% chance of drawing a heart from this deck. And we're talking about drawing a heart, that's 1 heart. So we're drawing 1 card here. I just wanted to point out when we say A, we mean 1 card. C, what is the probability of drawing a card that is not a heart? Now there's 2 ways we could do this. One way is we could use the raw data. We know there are, if you count them, 3 other suits that are not hearts, 13 cards in each of those, which means there are 39 cards that are not hearts. That's 39 out of 52. which when we calculate that is 75%. The other way we could calculate this same answer would be to think about the complement. It says not a heart. The probability of not being a heart would be 1 minus the probability of being a heart. So I could say 100% minus 25% because I calculated the chance of getting a heart earlier, just in the question above. So 100 minus 25% is also 75%. So I can use the complement rule or I can use the raw data and get the same answer either way. Question D, what is the probability of drawing a face card? Now, a face card is basically a jack, a queen, or a king. If you actually see the card, usually they have people on them. So that's why it's called a face card, because there's a face. So there are 3 face cards in each of these suits. So 3 4 times is 12 face cards out of 52 cards total. So you've got 12 out of 52 chance, which is approximately 23.1% chance of getting either a jack, a queen, or a king, a face card. What is the probability of drawing a queen of hearts? Now, we're being very specific. We're talking about a queen specifically of hearts. There is only one queen of hearts in the entire deck. Only one card that is both a queen and a heart. So that's 1 out of 52 possibilities. 1 divided by 52 is a chance of 1.9%. So you've got a 1.9% chance of getting specifically the queen of hearts. What's the probability of drawing a queen or a heart? So this is a little different because we're talking about it being either a queen or a heart. Now there are 4 queens in the deck and there are 13 hearts. So you might say there's 17 ways of doing this, but what I want you to kind of recognize is that there is some overlap there because there is a queen of hearts. So we want to make sure we don't include overlap. So looking at the raw data can actually help you do that. We look at this deck of cards, there are actually 12 cards that are hearts and then 1, 2, 3 extra queens. So that's, I think I said 12 by accident. There's 13 hearts and then 1, 2, 3 more cards that are queens. So that would be 16 total cards that are either queens or hearts. That removes the overlap of one card, and there are 16 out of 52 cards that are either hearts or queens. So 16 out of 52 gives me a percent of 30.8. So a 30.8% chance of drawing either a queen or a heart. Last question. What is the probability of drawing a queen given that you only draw from the face cards? So remember when we talked about perspective, when we talked about empirical probabilities, here we're changing our perspective. All of the other questions here asked about the entire deck, or it was implied that we were looking at the entire deck. Here we're only looking at the face cards, which means we're only looking at 12 of the cards. And the probability of drawing a queen, if you're only looking at the face cards, there are 4 queens. So 4 divided by 12 gives me a 33% chance, or 33.3% if I round at the first decimal point. So you have to sometimes consider perspective, and that will often be given to you in the wording.